Welcome you all to our first discussion of the beginner notebook. So today's session, we thought of focusing on mainly discussing your questions and then uh, going through some of the solutions or maybe some similar answers to the problems in the notebooks rather than revealing all the answers, because we will be providing you a submission link which will be active till Wednesday midnight, so you can I think you can learn from today's session as well and work on your notebook and then submit the notebook by Wednesday. So we will send this link to the WhatsApp group as well. Since there's only a few of you, um, if if you have any questions that you guys want me to go through first, feel free to ask, or else I could go through some solutions for the tasks in the note. Did you all try to solve any of the tasks, or did you all attempted the notebook? Okay. So then I will proceed with working through some solutions. So let me share my screen. If you have any questions, feel free to drop them in the chat or maybe raise your hand so we can unmute you and we can ask the questions directly. So this is the platform that I am using for today's session. You don't have to use this. You can stick with Collab. That's totally fine. The only thing is, if you are going with Collab, you will have to install the Qiskit and Quantum libraries. Here, most of the time, those are pre-installed. It's like if you go with Collab, some of the scikit libraries and ML libraries are pre-installed. But if you go with a local Jupyter notebook, you have to configure your Python environment with the necessary libraries. Similar to that, this platform has the Quantum libraries pre-installed, and you can spin up a free virtual machine here if you have an account. It's free to create. You don't have to provide any. Okay. Let me try another one. Just give me a second. Okay. Yeah, sometimes it might have certain issues because this is not a full-fledged VM platform that is like Collab. This is specifically for quantum tasks. I mean, a specific company that is developing this for quantum learning and stuff. So it's not as good as Collab, but it's somewhat flexible with the quantum libraries and stuff. That's why I'm using it today. Just give it a minute, Christina. Okay, so I will go with notebook. All right. So have you all gone through the notebook yet, or are you guys yet to look at the notebook? What's your status with working through the notebook? Anyone who has tried the notebook? Okay, one person. What about others? All right. So for the two of you who joined now, we will be providing the solutions notebook on Thursday. So we will keep the submission link active till Wednesday, and we will provide you the correct solutions by Thursday. Here I will show you some similar answers, but they are not necessarily the correct answers for the given task. This is just to show you what kind of a solution that we are expecting here, and if you have zero experience with this, to give you some kind of a framework to look at and see how this kind of a thing could be done, or how this kind of a task could be approached. So I won't read everything. So first you have to install the necessary libraries, especially if you are running this locally on a Python environment or in a Jupyter Notebook environment. You should have these libraries installed. So I think I should have this installed. Yeah. So that's the good part with the Qubit, and you have to import them first. That's the setup part. I think it would be easy. So I'm not going to go into much details with that. Now we come to the first task. So I think we mentioned about these during our first two sessions about Pauli operators or single qubit operators. So these are, you can think of these as mostly rotation operators. For qubits, you are rotating by a certain amount or a fixed amount. So here, what we are asked to do is create a custom operator using these single qubit operators that will act on multiple qubits rather than just one qubit. All right. So if we go with, let's say, Pauli X, let me show you what the Pauli X matrix is. So the Pauli X matrix looks like this, and the Pauli Y matrix looks like this, and the Z looks like this. So Pauli X is almost similar to a NOT gate, so that's why we call it the X gate. So similarly, the other ones also have 2x2 matrices. That means it is taking one state and transferring it to another state in the context of qubits. But here, what we are looking at is how to construct an operator that could act on multiple qubits rather than a single qubit. So how you create such an operator or such a matrix is by using this command, and these xi or xy, z, and I are Pauli operators that are like inbuilt in the Qiskit system. So if you want to combine any of these, let's say you want to create a gate that adds xxx to all the qubits. So you go like this, and then it will create a matrix. Sorry. Okay. So I forgot the quotation mark. So yeah, this is what xxx looks like, which means I'm adding x gates to qubit 2, qubit 1, and qubit 0. So similarly, if I wanted to have an x and an I represents the identity gate. That means basically you are doing nothing. So imagine you wanted to, let me go to the composer. So just give it a minute to load. Okay. So let's say I wanted to create something like something that could act upon all 4 qubits as layers. Okay, so what I mean by that is I'm trying to write a program to automate the task of adding these gates. So let's say I wanted to add an X gate and I wanted to add a Z gate. And now I need to add an X gate here, an Z gate here, and the Y gate here. Okay, so one way you can do that is with these Pauli operator, creating Pauli operators. So how you do it is this way. So here, what I did was I just added an X gate, but here I didn't add any gate, but you can't represent that in this specific gate creation scenario. So for that, you have to add an identity gate. If I wanted to do the exact same step, I would have to do X, I, Z, I. So now I'm creating a 4-qubit operator that acts on 4 qubits. The I gate does nothing, basically. For a single qubit, it does nothing. So I hope you have the idea for this task. So I think it would be fairly straightforward to do the given task. So again, I'm telling you to ask any questions if you have along with these tasks. So I'm going to go through all the tasks, most of the tasks, and provide you some examples to get an idea on how to do that. So I'm going to the next section. Now here, we are asked to use single qubit gates, not only the Pauli XYZ operators, but also SNT operators, which are phase gates, and do something with a single qubit circuit. So first we are asked to put the qubit in state 1. I think that you guys should know by now. We can add an X gate to put a state from 0 to 1, or vice versa, 1 to 0. And then we are asked to apply a single gate that applies a 5/4 phase shift to the qubit and print the circuit's final state vector in the direct notation. So here is how you get the state vector of a circuit. So first I created the circuit of a single qubit, then I added some gates, and then here's how you get the state vector, and you assigned it to a variable. And here's how you draw the state vector in LaTeX format. So you get all the direct notation. So the gates I have added here are not necessarily the ones that would create the required state of creating, like, the NOT gate part is there, but adding a 5/4 phase shift is not correct. This is also a phase shift gate, but it's not by a 5/4. So you can do a little bit of research on that, on which gate would add this particular phase shift. So this is not a phase shift gate, but if I add the Hadamard gate here, it would give me a state like this. So you can search on the Google or maybe on anywhere else and find which gate gives this phase shift. So before moving on to the next section, I wanted to highlight these 2 resources for you guys. First one is the IBM Learn platform. You can use this to like go through structured materials, which is basically there are certain courses that gives you the basics of quantum information, and also some tutorial notebooks and modules and stuff. You can go through all this if you go to this platform. And this is the official documentation of Qiskit. If you are not familiar with documentations, it's an essential part of I mean, computer science or even in classical computing, it's an essential part, right? Whatever technology that you are using, you should be familiar with its documentation and how to go through a technical document as well. So here you have all the necessary things about Qiskit, since they have gone through a major update to the platform, like to the entire ecosystem of Qiskit. These are all updated. Earlier, there were some problems with some of the documents being outdated, but I don't think it should be an issue now. So you can find all the instruction to how to start this, how to create your environments, how to install Qiskit in various environments, and how to configure your development workflows, how to access the Quantum platform, how to create your accounts, what are the basics of Qiskit, and how the complex parts like transpilers, visualization parts, and all these additional add-ons and all that stuff work. So if you have any doubts about a particular thing, how a particular function works inside Qiskit, so let's say if we look at this function, this particular state vector functionality, if you want to find more about that, you can go to the documentation and also use the search. So you have you can go to this. This is for the IBM, the Qiskit Composer. So you can find out what it does, and if you wanted to go with something else, you can find about pretty much everything about the Qiskit's functionalities. Right. So back to our tasks. The third task, it is about superposition and block spheres. So now we are no longer working with the standard Pauli XYZ gates because they have fixed rotations. Now we are trying to work with some rotation gates with custom rotation angles. So you can have rotation X, rotation Y, or rotation Z, and how you measure the superposition. Just keep in mind that only the basic equal superposition state has this state vector of this is basically 1 over square root 2 and 1 over square root 2. So only that equal superposition has that value. It doesn't have to be a 50-50 superposition. It could be anything. So using these three gates, you can have any kind of superposition. So here, what you are asked to do is basically that. So you want to have a state that is approximately 14.6% measuring 0 state, and the rest measuring 1. So I'm not doing that one here. I'm doing a different one. So you can find out how to do this. Here we are asked to do this with RY gate. So you are given the equation, you are given everything. So you can find out what the exact theta should be. Here I am using 5 times pi over 8. So if I use 5 times pi over 8, I'm going to get 0.30 or 30.8% 0 state and 69.1% 1 state. So maybe you can try putting some values, or you can do the calculation using this equation and find out which theta you should use here. So again, I'm using the state vector functionality to get the state vector, and I'm finding the probabilities here. Earlier, I drew the state vector as it is. Now I am finding the squared values of these probability amplitudes. So I'm getting those values from this state vector variable, and then I'm printing those, and then finally I'm plotting the blood stream. I think you are familiar with these because in the Qiskit introduction session, Lisita did most of these. But if you are in doubt, you can use the documentation or the quantum learning platform. And also we will provide the notebook with the solutions by Thursday, once your submissions are over. So moving on to the fourth section. So here we are trying to work with multi-qubit operations and entanglement. So I hope you remember from my session that entanglement is key to achieving quantum advantage or any kind of a quantum advantage. So it is essential that we learn to use multi-qubit gates like CNOT. If you don't remember, CNOT gate, this is the CNOT gate. What it does is it uses this target qubit, sorry, the control qubit, and does something based on its value to the target qubit. So essentially what it does is if the control qubit is 1, it is going to change the target qubit and apply an X gate to the target qubit. So basically a bit flip to the target qubit. So here you are asked to create the most fundamental entanglement position and equal Bell state with this state vector. So that means it's in an entanglement with 0, 0 and 1, 1 state. But here I have not done that. I have done something else, but I think it's very straightforward for you to identify which this state is, because these are this notebook is covering some of the most basic concepts. Even if you just Google this or ask from ChatGPT or whatever, it should know what this means. So this is a very fundamental state. If you search what gates should I use to create this Bell state, you will find it out. And again, here this statement is also mentioning which gates you should use. So here it is asking to create a 2-qubit circuit, but I have created a 3-qubit circuit. So try to adapt that to whatever thing that you need. And the only difference here is for this gate, the first parameter gives the control qubit, and the second parameter gives the target qubit. So that's the difference in multi-qubit gates. You have other multi-qubit gates like control Z and some custom gates you can develop with control unitary gates and even 3-qubit gates like Toffoli. In any case, the first parameter gives you the first target, sorry, the first control, and the last parameter gives you the target qubit. So in the Toffoli's case, it should be something like 0, 1, 2. In this case, these two are your control qubits. You have 2 control qubits, and this is your target qubit. I think it's covered in this task, but just for your knowledge. So here, what we are using is the display function with QC draw. Even if you use the qc.draw and MPL, it should draw the circuit, but it's good to use the display function as well. And there are some other ways that you can draw circuits, especially if you are maybe writing a research paper, or maybe you want to add this to some documentation and you don't want to add it as a picture, then you can generate this text version of it with Unicode characters. And also you can do the LaTeX version of it. Yeah, this is the LaTeX version of it. If you are referring to research papers, you would mostly see this rather than the matplotlib version of it. It's quite nice to have the matplotlib version, but in literature you would mostly see the latex version or the text version. So yeah, that's just another addition to your knowledge. And these are standard stuff. Now you know what the state vector is and how to print the state vector. So moving on to the next section, feel free to ask any questions. Again, a reminder. So now we are looking at how to build a circuit and how to draw a circuit. Now I have actually covered this part, so I won't go into much details about this. Same standard stuff. You can have MPL, text, or latex. And also, here we had the 0th bit at top. You can have this additional parameter for the draw function as reverse bits true. In that case, you would have the 0th bit at the bottom and the highest or the most significant bit at the top. So that's based on your preference. Again, as I mentioned, you don't have to use the display function. You can just use this QC draw as well. It's just your quantum circuit name and having this draw function. Right. So up to now, is it clear for you guys? Do you have any questions up to now? Okay. So I hope it's clear. If you have any questions, you can ask, because this is basically a Q&A kind of a session. So it's not about going through some content and teaching you stuff, but mostly about clarifying any doubts you may have and answering your questions. So this is something additional that I'm doing here. If you have any questions, drop them in the chat or unmute and ask. So now we are moving on to something a bit advanced compared to what we have learned so far. So now we are looking at dynamic circuits and classical control flow. So if you are familiar with classical computing, I mean, most of you are familiar with classical computing, you should know that there are control flows or control functionalities like if, else, which, and all these loops and stuff. So we talked about how fragile these quantum states are and how these quantum states collapse when we try to measure them. But there should be some way to do something in the mid of the circuit by measuring something, right? I mean, if you always have to create a circuit that only measures at the end, and you have to do all these things assuming this would happen and that would happen and all that, then it is not suitable for larger tasks, right? Because you should be able to break things down into smaller components. So that is essentially the idea of classical control flows. So I will execute this circuit and show you what I mean by that. So here, what we are doing is basically, this could be a circuit with maybe many number of gates or of any length. But the focus area is this, because what we are doing here is just forget about this qubit. This is just an addition. But what we are doing here is we created a superposition state here with the 0th qubit, and then we measured it to a certain classical bit. So I created a quantum circuit with 3 qubits and 1 classical bit. So this means I have 3 qubits in my quantum register and I have 1 bit in my classical register. So if you are defining it that way, you have to define it as classical register 1 with 1 bit array and 3 qubit array. So now I have added an X gate to the first qubit, a Hadamard gate to the 0th qubit, and also a measure gate to the 0th qubit, and that value will be stored in the 0th classical bit. I'm reminding this. Okay. So now this is the part that we want to talk in classical control flow. What this does is have a classical if condition embedded into the quantum circuit. So what it does is, since I measured it here, the state has collapsed, but only for this qubit, right? When I measure this qubit, it is not going to affect these other qubits. The collapse happened only to this qubit. So I collapsed that state and I measured it. And here, using this classical qubit, I am checking whether the classical bits, so I'm storing in 0th classical bit. So, okay, one question. Is this properly visible for you guys, or do you want me to zoom it?
I
Is it
think it's
better now?
better to zoom. Yeah.
Yeah. Okay. Sorry about that. I hope it's better now. All right. Okay. Back to the if condition. So what it is doing here is checking whether the 0th classical bit or whatever the classical bit that we want to check is equal to 1. And if it is 1, then I am going to add a X gate to the second qubit, or the second qubit, the from 0 index second qubit, right? So this is basically a classical control flow, which means it is not a C0 gate. I mean, we are not checking if the qubit is at one state here using a quantum gate. What we are doing is actually measuring it. We are not relying on the intermediate superposition state. We are actually measuring it, and we are using that actual measurement result from a classical bit and applying a gate, any kind of gate, based on that information. Okay, so we are not collapsing the entire quantum system. We are just measuring 1 or 2 qubits and taking their values and applying some other gates or some other quantum circuits based on those values. So I hope that's clear for you guys, because I can maybe add another gate here. So let's say I wanted to add use the 0. It should be possible. Yeah. So you can see, based on the measurement of this, I am adding this entirely new circuit. So that's one thing with the classical control flow. Now we are moving on to the next part. Okay, so parameterized ones, we will get to that once we do the simulations and results. So here again, these are basic stuff. Creating a quantum circuit with 3 qubits and 3 classical bits, applying a Hadamard gate, applying a C0 gate with 2 as the control and 1 as the target, then measuring all 3 qubits. Then I'm using okay, so we have a question. It depends on your application. So let's say now I can use this as maybe a new qubit, because this one is anyway going to be 0 or 1. Okay, so let's say one thing you can do is, let's imagine it this way, right? I have a quantum computer with maybe 5 qubits, not those 100 qubits and all that one. And I have only one execution round, and I have to create a circuit that does something multiple times. So in that case, I can add another Hadamard gate here and another measurement here, and likewise, which means I can use the same qubit, but in practical sense, it doesn't make much sense, because these devices are made to run multiple shots of the same circuit. So if you are reusing that qubit for application of the same circuit multiple times, it doesn't give you any advantage, rather than it only adds complexities, because let's say now I had a equal superposition state, and I can't be sure in which state this qubit would be when it is measured. It could be either 0, it could be either 1. So maybe in that case, I would have to apply another reset gate, like this 0 1. Okay, so let's say I added a measurement here. Okay, I had a Hadamard here. Once this is measured, after that, this could be either 0 or 1. So if I have to always start from the 0th state, then I have to add this reset gate, and then again I can add the Hadamard and measurement gate. But it doesn't make much sense, because it is going to increase the depth of the circuit when you can just you can remove all these three and just increase the number of shots. Okay, it's asking me to sign up. I will do it later, but you can increase the number of circuit shots there, and like here 1024, we are normally running for 8,000 or some thousands of shots, so it doesn't matter much. But if you really want to do that, you can do it, because I have seen it somewhere for a quantum random number generator. So in one research paper, that person has proposed something like this. Let me quickly do it, demonstrate it. So what that person has suggested is basically this. So you create a equal superposition. So you get 0 or 1 from this, and you add this like 128 times to get a 128-bit key. So you don't actually have to do that, because you can remove all these stuff and just run the same circuit 128 times. So it really doesn't matter. But again, to add another perspective, if you want to do something based on this measurement for that particular qubit, then that is also possible. It's just the state has collapsed from an intermediate state like this to just 0 or 1 with 100% probability. That's what you have to keep in mind. There is no limitation to using it. I hope that clears your question. Okay. Let me know if you're not clear about that. So moving on to this part, visualizing quantum states and results. So we were talking about up to this point. You guys know up to this point. And now here I'm using the backend, the AR simulator. And okay, okay. I'm using the primitives to the sampler primitive to run this. So optimization level 1. I think all these were explained in the introduction to Qiskit session, right? Is it? Okay. So I will quickly go through that. This is basically what your backend is. You can have an actual quantum hardware here, but here we are using the AR simulator. You could have another simulator like state vector simulator or anything like that. But AR simulator is best for most of the beginners because you can have sort of a more realistic feeling of using a quantum computer because it is not going to give you the exact probabilities. So if I run this, you will see that you are going to get, I mean, this is at a state of 50% this and 50% this, but it gives you some noise and random values based on its noise models. So you can get a more realistic kind of a feeling when you use the AR simulator. And this is just the sampler that we use. So maybe you can think of this for now as, you know, when you are writing a hello world application in Java or C, not Python, but if you are writing something on Java or C, you have to write some boilerplate or some prefix codes to set up the environment and all that stuff, right? So import the necessary libraries to output to the screen and all that. So you can think of this entire block as something like that with certain parameters. This is something for the transpiler. Again, this is also for the transpiler to identify which backend we are using and how much the circuit should be optimized. And this is to give an idea about how many times the circuit should be run. And then this job is important because the idea here is not just for the AR simulator, but we are running these experiments on a job queue kind of a job queue like method where you submit a job to the backend and it gets queued for that specific quantum hardware. And once it is executed, you are going to get the result back. So you should have some way of storing the job and retrieving its result and then analyzing its result. So it is the same for the simulator as well, but you are going to get the results instantly here. But if you are using a real hardware backend, you are only going to get a job ID, and using that job ID, you have to get the results and then do whatever analysis that you are doing. So this is a basic analysis of plotting the histogram of whatever values you are getting as output. So again, this is not the exact Bell state that you are required to create. This is the same Bell state that we created above. Again, in that also I didn't use the correct circuit. So you can easily find out which gates you should use to create this Bell state and edit the necessary functions to achieve that state. So moving on to another important part, parameterized quantum circuits. So now we started with something very limited, like Pauli XYZ gates with fixed rotation parameters. You could just bit flips or do bit flips or phase flips. And then we had some other gates like S and T with, again, fixed rotation angles, but different ones. So we could achieve some intermediate states with those. If we go with S, it's not going to do anything. If we go with 3 or so, it's not going to do anything because this is a phase shift. But if I add like this, then it might do something. Yeah. So now you can see we can achieve some more states with these additional gates. Then we moved on to these rotation X, rotation Y, and rotation Z gates, where we could use like any custom angle for the rotation parameters. And then we had entanglement and all those other stuffs, and also classical control flows with classical leaf phases. And now we are coming to parameterized quantum circuits, where you are defining a quantum circuit as a function. Okay, this is a simplification or like an analog, but it is not the actual thing. You are not representing a quantum circuit as a function. But what I'm trying to explain is, when you have functions in Python or something, you can just pass some parameters to that function and use it for whatever need that you can, whatever need you have for different inputs. Similarly, here what we are doing is we are defining a circuit in a parameterized way. So the next time we want to use that circuit with a different value for the angles, we can use the same circuit definition and just change the angle parameter only. So here's how you do that. You can define a parameter. You can put whatever character you need, and you can name it whatever angle name you want. And then you can create the quantum circuit as usual. And then you have to, I mean, it doesn't have to be all rotation gates like rotation Y, rotation X, rotation Z. You can use other gates, but the important part is whatever gates that should be parameterized should use this format. I mean, you can have QZX as well. It doesn't matter. The only important part is, if you need some gate to be parameterized or its rotation angle to be changed based on the input, you should use this format, and you should use the RY, RX, or RZ gates. So here I have defined this as theta 0, theta 1. So this is going to draw you the original circuit. So as you can see, I could have fixed gates, and I can have these parameterized gates. So this is my, you can think of this as my function definition. So this is my circuit definition. So I have defined it based on theta. And now I am using that circuit definition and assigning parameters to that as theta to be equal to this angle parameter. And now when I draw the new circuit, it is going to have those values. So as you can see, you can define a circuit that could be used multiple times with different parameters. This is very important in quantum machine learning and related stuff, because what you are doing is basically refining a parameter by putting it through the circuit multiple times and doing some classical analysis, and again calculating the theta value, and then again putting it back to the quantum circuit, and some process like that. So especially for those tasks and some other optimization tasks, this is really valuable. Up to now, is it clear for you guys? Any questions? Okay, feel free to drop any questions on the chat or just unmute and ask. So if there are no questions, I'm going to move on to the next section. So this I actually explained in the previous one as well. So can define a Python function that accepts the angle and pass it to the game. Well, I think that complicates it a bit if you are going to work with large circuits, because yes, you can. I mean, you can have some. Yeah, you can have some theta here, and what you're saying is you could have a separate Python function that manages this variable, right? So yes, that should be doable. I haven't. Maybe I have tried it that way. I haven't tried it recently. It should work, I think. But what it gives is basically an easier way for you to do it from within the circuit itself. So you can create now with this function. What happens is you can have this small circuit. I think there are certain ways where you can combine circuits and let's say add circuits as parts of circuits. So it is not about just let's say now if I wanted to have a 4-qubit circuit, I could use some 2-qubit circuits and add them as blocks here as just functions, separating them with barriers. And I could add them to these 2 qubits. I could add them to these 2 qubits. If I'm, let's say now I have this 2-qubit parameterized circuit, right? So I could add this to these two, and then maybe add a barrier and have some 4-qubit gates or 3-qubit gates or whatever circuit I have. Then I can also add the same previous circuit to these 2 qubits and these 2 qubits and so on. So in that case, I think it complicates stuff if you try to do that with Python functions, because I mean at the end of the day, it's all about assigning some matrices. Okay, so when we are doing these X gate additions, RY gate additions, and all that stuff, what we are essentially doing is telling a transpiler to, I mean, telling a transpiler what metrics to add. So it is just some simplifications that is provided by the Qiskit platform. So this gives you an easier way to do the parameterization rather than handling all the complex logics of let's say if you wanted to add a circuit here and here, then you have to have separate functions for those and all that stuff. So why bother with all those functions when Qiskit is providing this? Or you can think of it as the people who develop these functionalities had the same problem, and they came up with this functionality to provide an easier way of doing that. Does that answer your question? Okay, awesome. So moving on to the transpilation and optimization part. So I think this should have been explained. I also explained it a bit anyways, I will show you this diagram. We try to find the, okay, so I will use this one, or maybe I will use this one. Okay, or this way. So this is actually how the qubits are placed inside the quantum computer or a quantum chip. So you may remember that I talked about this briefly in my session, that you can't entangle whatever qubits you need. So I showed you by executing a circuit and showing how the transpiler has moved around the qubits that I have fixed, and added some other gates and done some stuff to transpile it to the specific quantum device. So the idea here is you can't entangle whatever the qubits you need, and also these colors signifies some error rates and all that stuff. So some gates can be applied between these two or these two, but maybe it's better to apply the same gate between these two rather than these two. So for those kind of things, Qiskit has developed this transpiler functionality where it knows all these parameters and all how each of these qubits are connected. So what you are doing as transpilation is basically uh, translating your quantum circuit to a device specific qubit map. Okay, so when I do this, it should show me the mapping of the transpilation. So let's give it a bit of time, because it shouldn't take that much of time, because the fake one should be built into this. Let's just give it a minute. So this one is not a real backend. It's based on I think some older quantum computer, but it's a kind of a fake backend that is there for you to try out this. I think it's probably taking some time, because session 3, or it's just idle. Sometimes this Qubit platform has certain issues with, let's say, reliability of their VMs. It's easier than Collab, but it has some issues with the VMs. So yeah, if you don't really want to bother with all those things, you can stick to Collab. Let me quickly execute this one again, and go to this part. Okay, so it was executed anyways. So this is what it has given us. So I created this circuit with H gate and CX01 and 21. That means basically I'm doing this 01 and 21. That means I'm, yes, and we don't have this key. So I built this circuit, and this is the one that was transpiled. So it decomposed the H gate into three RC rotations and X rotation gates, and it also had the same C node gates, but it's different from what we did, right? So as you can see, the 0, 1, and 2 has been changed to 1, 2, 3. That's a different mapping of these qubits, but the result that you are going to get is mapped back to your own circuit, right? So the original depth, which means the number of gates in the linear fashion, is 3, but here the depth is actually 5. So transpilation is something that maps your circuit to the device structure. Hope that's clear. You can do more things with this, especially if you are doing complex circuits with hundreds of qubits. Then you have to start worrying about all these connections. But if you are doing some small circuits, then you don't have to worry much about those. So now we are moving on to Qiskit runtime execution modes, the sampler and estimator primitives. So I think these are more like concepts that these are anyway conceptual questions. That means these are stuff that you can refer to the documentation and learn. And also I'm pretty sure that these were covered in the Qiskit session as well. Not in my session, but this session. So I'm not going to go into details about this because this is not just quantum computing. It's about the Qiskit SDK and some specific functionalities that they have. So you can refer to the documentation and using the sampler primitive. And yeah, we did this before, so it is the same as before. Again, this one is using the estimator primitive rather than the sampler primitive. We did something with the sampler primitive, so you can refer to that as well. Again, some theoretical concepts or theoretical stuff. I mean, error mitigation is a huge branch. You have to error mitigation is not something that I can cover within a couple of minutes. So what they are looking for here is actually to explain you what are some error mitigation techniques that they have implemented in the Qiskit platform and how they can be used. So I'm going to skip those because you can refer to the documentation to understand these better. And these are again conceptual questions. No coding is required. So now we move on to OpenQASM. So I hope everything is clear up until now. We will quickly finish this with OpenQASM. So we talked about Qiskit, but Qiskit is not the standard of quantum computing, let's say. Qiskit is the most used language, but it is not the one that is agreed by everyone. So OpenQASM is something like assembly that we have today. I mean, assembly is actually device specific. If we look at it from, let's say, classical computing perspective, x86 or ARM assembly and all that are very different. But if you look at RISC-V or something, then there are some similarities. But I mean, the standard is that there is some kind of a language that you can translate everything down to. So whether it is C, whether it is Python, whether it is Java, or Rust, or it doesn't matter. You have to translate everything into assembly language to run it on a classical device. Similarly, the OpenQSM standard is actually the quantum assembly language, where it is like the standard that everyone is trying to compile their languages to. So Qiskit is Qiskit is transpilable to OpenQSM, and OpenQSM is OpenQSM strings can be converted back to Qiskit. So OpenQSM is pretty straightforward. So this is OpenQSM 2.0. So basically, this QLib one ink is basically the definition set of these gates and all that stuff. If you want, you can refer to the OpenQSM documentation as well. Yes, I think it should be this. There is a nice page with like graphical interface. I will send you that in the group later, but you can refer to the OpenQSM documentation even here on its GitHub. So they have all the definitions for each of the gates and almost everything that is required for a fundamental quantum computation, not just device specific ones, because IBM has different kind of quantum computers, and other people have other types of quantum computers, be it annealing, neutral atoms, or photonic, or whatsoever. So you can think of this as a more of a standard for quantum computation. So here what it does is, here we are looking at OpenQSM 3.0. It's a bit advanced from 2.0. It has some loops and all that functionalities. Previously, you didn't have all that in OpenQSM. OpenQSM was mainly only for adding gates and doing that stuff. But now you have some control structures within OpenQSM. That's the main addition to OpenQSM 3.0 compared to OpenQSM 2.0. Here they have only included OpenQSM 2.0. So you can see this is the Qiskit version, and this is its OpenQSM version. So here what we are doing is including the library for the sorry. Okay. Yeah. So here we are training that it's an OpenQSM 3.0, including the library, telling it what the qubit register size is or the quantum register size is, then the classical register. Then you can add whatever gates you want here, and you can measure it. This is basically your OpenQSM program, just like here, your OpenQSM program with the measure one. And if I add the measure gate here, it should add that. Okay, so this is OpenQSM 2.0. Don't get confused with that. So this is OpenQSM 3.0. So you just have to add 2 gates to create this well state or something, I think. Yeah. So then you can print it. This is just for printing, but here what we are doing is basically importing that OpenQSM 3 string as a quantum circuit in Qiskit. So as you can see, same stuff as before up to the classical register. Then I have added the H gate. Then I have added the control not gate, control Q not, and target Q1. Then I have measured one. Then I have measured all. That's pretty much it for my circuit. And then I have converted it to the Qiskit circuit using this feature in Qiskit, and I have used the draw function from Qiskit. So yeah, this is something just for your knowledge. I don't think at the basic level you would be coding in OpenQSM. But if you are trying to build something like a simulator or some other kind of a tool, then you might have to go with this standardization. And then it talks about the IBM runtime API and how to run this on a real device. It is fairly straightforward. You can add your API keys here and execute it. So since this will take time anyways to get the result back, I'm not going to run it now. So that covers our first notebook. So do you guys have any other questions or things that you are struggling with? Feel free to ask if you have anything related to the notebook or any of the materials that we covered before. If you don't have any questions, we can conclude the meeting. So I will wait till 9:25 in case if any of you are typing a question. Is there any limitations in using OpenQSM? Yes, there are a lot actually, because let me try to find it. Okay, so I mean, I work with a team of a few others from UCSC on building a quantum compiler. Not a compiler, actually, a compiler and a simulator. So similar to Qiskit, basically the Qiskit composer. So in that case, we had to rely on OpenQSM specifications. Basically, to transpile it back to OpenQSM because we wanted to make sure whatever that we are running is standardized and could be verified with other libraries like Qiskit. There are other languages like Penny and all that stuff. So I think that is one of the biggest advantages or biggest use of the major use of OpenQSM as a standardization. But if you look at the OpenQSM language itself, uh, it is very limited. As I mentioned, only with the 3.0, it had these, I mean, these loops and conditions and all that stuff. Earlier, you had to just list whatever gates. I mean, if you are using Qiskit, you are going to use Python functions to add gates repetitively, right? Let's say you created a 5-qubit circuit, and you want to add Hadamard gates to all those qubits, and you are not going to say qz dot h dot h bracket 0, qz dot h bracket 1, and all that. One way you can do it is qz dot h, and you give the entire Python array. So, Qiskit has provided that functionality, but another way that you can use is you just define a for loop from 0 to 4, and then you say qz dot h I within brackets, so that it adds all those gates. But in the case of OpenQSM, you had to define all those gates one by one. There were no loops within OpenQSM until now. So now it has these arrays and all that. So it is somewhat advanced now, but as you saw from the composer, the Qiskit composer itself, it is also still using OpenQSM 2.0, and OpenQSM 3.0 is very new. So right now it has some additional functionalities, but still, if you look at something like Qiskit, it has built-in gates for, let's say, example, quantum Fourier transforms, or maybe even for things like Grover's search or Dutchess algorithms and all that stuff. You have functionalities that you can you have functions that you can call for that specific kind of problem. So if you wanted to define a QFT or a quantum Fourier transform circuit structure, there is a specific function called in Qiskit. So it's not just about adding the gates. Qiskit has noise models, error mitigation models, and other things like all these problem-specific definitions and all that stuff. But OpenQSM lacks that. That's why I compared it with assembly. I mean, it is essentially an assembly language. So in assembly, you have loop and some conditions and some very basic functionalities, and you don't have all these high-level implementations of stuff in assembly, right? But anyway, you are compiling everything down to assembly because at the end of the day, you have to run everything on the basic fundamental blocks. Similar thing with OpenQSM. You have all the fundamental blocks needed for a quantum computation. But if you look at something like Qiskit or even Penny or some other language like Microsoft's Q# or something, they have more functionalities than OpenQSM, similar to Java or something in the classical realm. Hope that answers your question. You can go through the OpenQSM specification if you are interested and find out what its grammar look like, what the language grammar look like, and everything about the OpenTython language. Any other questions? Or shall we end the session? If you have any question or if you are typing something, just raise your hand or we'll just conclude the session. All right, guys. Thank you for being here, and I hope you guys are following through the workshops and the self-study modules. So we will release the next self-study modules maybe tomorrow. So if you have already finished the beginner one, you can start working on that. Your deadline to submit the beginner notebook is Wednesday midnight, and we will provide you the solution notebook by Thursday. So if you have any, I covered most of it, so you should be able to complete the beginner notebook. In any case, we will provide you the correct solution for the entire notebook by Thursday, and we will do the same for other notebooks as well. So there is another intermediate notebook and an advanced notebook, and in the advanced notebook, just to give you some spoilers, you will be simulating some molecules and getting their ground state energy levels and stuff. So they will be a little bit advanced, but they will provide you the fundamental knowledge and hands-on experience you need to work for the hackathon problems. So yeah, good luck with that, and hope you guys are enjoying the process, and have a good night. See you all next week.